With this second video in Lecture 8, we're going to actually walk through an example of testing for whether there's a difference in means. So we're going to begin with what's called a two-sample t-test, and we're going to learn a little bit more about this test in a moment. But let's start by thinking about an example of where we might want to test for a difference in means. So this example comes from the STATA manual, and it gives a good illustration of how we might think about looking for a difference in means. So we're going to be thinking about the effect of a fuel additive on cars. And the way that the data has been collected for this is that we have a sample of vehicles, some of which have received the fuel additive in their gas, and some of which have not. And what has been done is these vehicles have been driven around and they measured the gas mileage for these vehicles. That gas mileage is going to be our main dependent variable. And we want to think about whether or not the fuel additive might have an effect on what the average gas mileage is. In other words, we might use the language of treated and untreated. We would say that treated cars are the ones that received the fuel additive, they received the treatment, and the untreated cars did not receive the fuel additive. We want to know whether or not that treatment makes a difference to our gas efficiency. So the mean for the treated cars in this little data set is 21 miles per gallon, while the mean for the mean for the untreated cars is 21 miles per gallon, while the mean for the treated cars is 22.75 miles per gallon. So the gas efficiency is higher for the cars that received the fuel additive. And we'll actually open this data set in just a moment. But this supports the idea that maybe the fuel additive is helping. However, we want to be a little bit cautious about these findings. In part, this is a pretty small data set, as you'll see in just a moment. And there's always some random noise whenever we're measuring something like this. So we want to know whether or not this small difference is statistically significant. Of course, that's one of the words we learned in the previous lecture. When we ask whether or not something's statistically significant, part of what we're asking is how plausible is it that if the fuel additive wasn't actually making a difference, that we might get a difference this large just because of random noise. We just have a small sample. So maybe if we had a larger sample, we would see that this difference would disappear or get a lot smaller if this was just a difference that we got sort of because of dumb luck. Again, there's always imprecision whenever we're trying to measure something like gas mileage. And so we want to see, is this difference bigger than the kind of difference we would expect just because of the imprecision that we get whenever we're running an experiment like this? So let's talk a little bit more before we go through the rest of this example about what we're doing conceptually here with a two-sample t-test. So there's lots of hypothesis tests that we can do, and there's multiple ways to conduct a hypothesis test for this particular research question. But we're going to focus on a two-sample t-test because it's one of the simplest ways to conduct a hypothesis test for this kind of situation. It would also be possible to conduct an equivalent test that would give us the exact same results, the exact same p-value for a hypothesis test using regression. Of course, regression is a tool that we talked about a while earlier in the semester when we were learning about relationships between two continuous variables. It's actually possible to use regression to study differences in means across groups. And this is covered in chapter 12 of the textbook, and we'll come to this later on in the semester, talk about it in more detail. But for now, let's focus on the two-sample t-test. When we use a two-sample t-test, conceptually what we're doing is we're treating our two groups, the group that got the treatment, the group that didn't get the treatment, as separate populations. In other words, we imagine one population where all of the cars receive the fuel additive and one population where all the cars don't receive the fuel additive. This is one of those cases where it's a little bit difficult to conceptualize exactly what the population is. It's actually a hypothetical population, as opposed to pollsters who often have a very concrete population in mind. So we're thinking about two hypothetical population. One population where all cars receive the fuel additive and one population where all cars don't receive the fuel additive. In the same way that we're thinking about there being two separate populations, we think about there being two separate samples. Essentially, our sample that we collect, that we'll see in Stata in just a moment, has been divided into two separate subsamples. One that corresponds to each population. So, in other words, we have one sample of cars that didn't receive the fuel additive and one sample of cars that did receive the fuel additive. In a two sample t test, we're going to compute the difference in the means between our two samples, and then we're going to see whether or not this difference is big enough that it's more than we would expect just from the random variance within the sample. We learned a little bit about degrees of freedom before. This is how we actually compute the degrees of freedom. And that's not necessarily a detail that you need to know by heart, because this is something that Stata will usually do for us automatically. But I did want to show you how degrees of freedom are being calculated. In this case, we think about having two samples, right? One for the treated, one for the untreated. So our degrees of freedom are going to be equal to those two sample sizes added together. In other words, the size of our whole sample rather than just the subsamples. And we're going to subtract 2 from that amount. Before, we had an example where we subtracted 1 from the sample size to get the degrees of freedom. In this case, we're going to subtract 2. But again, this is probably not something I would expect you to know for a test. This is just something that is good background information to hear once. So let's get back to our example. Our null hypothesis is going to be that the two means are equal. And you can see that I've represented these two means by using mu sub 1, we could say, and mu sub 2. In other words, I said that we're acting as though we have two different populations. These are population 1, population 2. The mean of population 1 is equal to the mean of population 2. That's my null hypothesis. And again, that's just a benchmark that we have in mind, right? Are we going to be able to have enough evidence to conclude that that's not the case, that there is a difference in fuel efficiency based on whether or not we have the fuel additive? So, in plain English, we could say that the null hypothesis is that the mean fuel efficiency is unaffected by the additive, or more directly corresponding to what we have written up there, the mean fuel efficiency with the additive is going to be the same as the mean fuel efficiency without the additive. All right. What's our alternative hypothesis? Well, our alternative hypothesis, at least if it's two-sided, is just going to be the logical alternative, right? So the logical opposite of our null hypothesis. So instead of these two means, the mean when we don't have the fuel additive and the mean fuel efficiency when we do have the fuel additive being equal to one another, now we're going to say that they're unequal to one another, that the fuel additive, in other words, makes some difference for fuel efficiency. Now notice, because we've done a two-sided hypothesis, we've said that the two means are unequal to each other. It could be that the effect of the fuel additive is negative. It could be that with the fuel additive, cars have a worse fuel efficiency. And that would still be corresponding to our alternative hypothesis. In other words, our alternative hypothesis would still be true if it turns out that the fuel additive has a negative effect on fuel efficiency. If we had created a one-sided test, we could say that we specifically are interested in whether or not, as an alternative hypothesis, the fuel additive has a positive effect. But for now, we're just going to focus on the two-sided test. All right. We're just going to stick with the standard alpha level of 0.05, like I said we usually do, unless we have a good reason to do something else. And this is the code that we can use to get this data read into Stata and then to run our hypothesis test. So I'm just going to copy and paste this into Stata. So let's do that and hit enter. And this is just downloading the data from the Stata website. You can see that this is how the data is formatted. There are 24 observations in here, and you can see that 12 of them treated is equal to 0, meaning they didn't get the fuel additive, and 12 of these observations got the fuel additive, so treated is equal to 1. And here's the different gas mileage that the different vehicles got, all 24 vehicles. So if we come here to our results for the t-test, we can see that we get a bunch of output. We see the mean here for the untreated observations. In other words, like we saw on the lecture slide, the mean gas mileage when we don't have the fuel additive is 21 miles per gallon. The mean when group or treated is equal to 1 is going to be 22.75. In other words, when these cars, among the cars that have the fuel additive, the average gas mileage was 22.75 miles per gallon. Here we see the difference between these two. In other words, the cars without the fuel additive have 1.75 miles per gallon lower in terms of fuel efficiency. In other words, their fuel efficiency is 1.75 miles per gallon less than the cars that got the fuel additive in our sample. So let me make a little bit more space so that we can see our p-values a little bit better. These are the 3 p-values that we get at the bottom. And like what we saw last week, the one in the middle is going to correspond to the two-sided alternative hypothesis. So this is the main one that we're going to focus on, because when we wrote out all our alternative hypothesis, we said that we were going to have a two-sided one. And you can see here, this is a reminder to us. The alternative hypothesis is that the difference is not equal to 0. That's a little bit different than how we wrote our alternative hypothesis, but it means the same thing, right? If the two means are not equal, then that means that the difference is not equal to 0. There is some difference between the two means. So here's our p-value, 0.1673, which we can just round to 0.17. So what are we going to conclude based on that p-value? We got a p-value of 0.17. Well, we always want to compare in any hypothesis our p-value to what? To the alpha level. Is 0.17 larger or smaller than our alpha? It's larger than alpha. If the p-value is larger than alpha, then what do we conclude? Well, when p is larger than alpha, we're going to fail to reject the null hypothesis. And anytime we fail to reject the null hypothesis, our results are inconclusive. In other words, we can't conclude that the fuel additive makes a difference because we have too small of a sample, and the difference between the two groups is too small based on our sample size to conclude that it's a difference that's actually being caused by the fuel additive and not just random noise that comes about when we try to measure gas fuel efficiency. If p had been smaller than alpha, I have a typo here, I'll change that in the slides I upload. If p were smaller than alpha, we would conclude that the additive made a difference for fuel efficiency, and there would be a statistically significant difference. So for example, if we'd gotten a p-value of 0.03, that would be less than alpha, and so this would be our conclusion. Again, this should read less than alpha, and I'll change that in the slides that I upload online. Okay. One other thing that can be nice to do sometimes when we're creating, when we're comparing means, is to create a graphic that shows us what the means look like. And so here's a command that we can use in Stata to be able to get a graph of our two means. But in order to be able to use this, we have to actually install a package first if we've never installed this before. So I'm going to copy this code because this is what we can use to install a package in Stata. Basically, Stata makes lots of commands, the company themselves, but they also want to allow users to write their own commands and then share them with others. This is a command that some other user, Stata user, wrote and then wanted to share with all of us. So the way that I can install this is to just run this command. In my case, I've already installed this command, so I just get a result saying that it was checking and verifying it's not already installed. All files already exist and are up to date. So in my case, it didn't do anything. So it never hurts to run this command because if you already have it installed, it will just say, oh, this is already installed. But if you haven't installed this package before, it'll be important to run that before you run this command. So now I'm going to copy and paste the command to create my graph. And let's see what happens. Stata is always a little bit slow, the first graph that it's trying to load. So let's be a little bit patient. Okay, here's our graph. You can see that this shows the average miles per gallon when treated is equal to 0 and when treated is equal to 1. If you'll recall, whenever treated is equal to 1, that means that the cars received the fuel additive. So we can see that the average value of miles per gallon is about not quite 23 miles per gallon, which corresponds to what we saw in our output, right? 22.75. So this is a graphic depiction of that. When we don't have the fuel additive, our miles per gallon is equal on average to 21 miles per gallon. So we can also see right here that we have confidence intervals. So in other words, this is saying, yes, there is some uncertainty, some measurement error or random noise in our values that we're getting for the means. And these error bars are plotting confidence intervals around the mean. In other words, if we were trying to estimate what is the true mean if we were to give everyone a fuel additive, this would show us our 95% confidence interval. And in fact, those confidence intervals are also shown right here in our output when we use the t-test command that we used earlier. So basically, this graph is just plotting the values of the means here and of the 95% confidence intervals here. But sometimes it's nice to be able to see this in graphic depiction instead of just staring at a table like this. All right, that's it for our first example of hypothesis testing. In the next video of this lecture, we're going to talk a little bit about the difference between hypothesis tests and confidence intervals.